Okay, we're going to look at graphs of relations and functions today. And just a few things before we get started, just looking at what the inequality signs are. So inequality signs are those less than, greater than signs. So less than points like this, I remember it because it kind of looks like an L if you were to tilt it a little bit. We also have less than or equal to. We have greater than or equal to, and then greater than. Some of you remember that the alligator is eating the bigger number, whatever it is that you remember, work with that. So to write an inequality that corresponds to a statement, replace the words that represent the inequality with the corresponding sign. So G is greater than or equal to 5. So greater than or equal to is that sign. So we're going to say G is greater than or equal to 5. X is greater than 3 and less than or equal to 2. So we have to say X is greater than negative 3, or we can say that negative 3 is less than X. We can flip it like that. We can also say, of course, X is less than or equal to, oops, I forgot my equal to there, 2. So to put these together, we have to write it in one statement where X is in the middle and our numbers are on the outside, okay? And so we write it with our smaller number to the left, larger number to the right. So when we write this together, we're gonna copy the signs that have that together. So X and 2, where X is on the left, we use this sign. Now, when X and negative 3 are related, where negative 3 is on the left, we use this sign. So this says that X is between negative 3 and positive 2. Things to note when you're writing two inequalities together like this. The lower value is always on the left, the higher value is on the right. And the signs, the inequality signs, point in the same direction as our original statement, okay? So, again, they have to point the same direction in this case, and you can always write it by flipping. So when you flip a statement, you can flip the sign as well. All right, continuing on, S is less than 4. And F is greater than 0 and less than 12. So F is greater than 0 and F is less than 12. Now I need to put these together where 0, F, and 12 are lined up. So in the same order, we have F is less than 12. Now, this statement isn't in the same order, so we need to flip it. So we'll say 0 is greater than F. Oh, sorry. What am I doing? 0 is less than F. Okay, I had to get my eraser working there. Okay, and then we'll input that statement as well. So notice that when a number is between, or a variable is between 2, we always end up with them pointing to the left, okay? So just some things that we've noticed over time of doing these inequalities. All right, does each graph represent a relation or a function? How can you tell? Well, every graph represents a relation because two things are related here. We've related the time with the number of species and the time with temperature. So these are both relations. Everything is relations when two things are related. Okay, so are they functions and how do you know? Remember, a function means that each domain can only have one range value. So we can't have 8 where we have a 5 and a 24. So it passes the vertical line test is what we've briefly touched on. So if I were to draw a vertical line at every data point, there would be no two data points stacked on top of one another. And in this case, it looks like that's the case for both. So both are functions. Because they pass the vertical line test or have one unique range value for each, domain value. All right. Which of these graphs should have their data points connected? Explain. So if we look at the data plotted here, we can have decimal points of time. So we can go between 6 and 8 hours. It's continuous. All right. So it could be 6:02 and a bunch of seconds. So there's lots of options for time. Okay. So time is a continuous data set is what we can say. However, in this case, we were plotting the number of species. Is that continuous? Well, not really. You can't have 4.32 species. It is a concrete number, okay? We call this discrete. This is discrete data, meaning there's no decimal value. I cannot connect these points. So whether that's from my X or my Y values, we have to consider, could this be a decimal point is really what you're asking yourself. Okay, so if that's the case, could this be a decimal point? We ask ourselves that here. Is time continuous? Could we have time in between 6 and 8 hours? Yes, this is continuous. Looking at temperature, could we have values between 2 and 4 degrees Celsius? Yes, we could have infinite number of degrees between that. We could have 2.1, 2.1000000001. So there's lots of options. Therefore, we will say that this is continuous data. And if it's continuous, technically, I can connect the points. You can either connect them with a ruler in between or like a bit of a smooth line. Okay, so you're asking yourself, could I have a decimal value? Could I have points between the graph scale? That will help you decide whether it's discrete or continuous. Continuous, the points can be connected. In discrete, the points cannot be connected. All right, a few other characteristics of our graphs. The domain of a function is the set of values on the independent variable. For this graph, the domain is what? So the independent variable is x. All right, so the x values or our input values, those are what we're talking about with the independent variable. So because this is not continuous data, we haven't connected the points. We have to list them independently. So what do we have for domain values? Well, we have x equals 0, x equals 1, 2, 3, and 4. So we will say that the domain is, and because it's a set of numbers, we use our curly brackets. We're going to list 0, 1, 2, 3, and 4. Close our curly brackets. Same thing for our range here. The range is a function of a function, is the set of values of the dependent variable. So that is our y values or our output. The range in this case, well, we have y equals 0. We have y equals 2, 4, 6, and 8. So our range is 0, 2, 4, 6, and 8. When the domain is restricted to a set of discrete values, the points on the graph are not connected. So we haven't connected our points, therefore we have to list each one individually. All right, we've kind of talked about this vertical line test already. I've used it because it makes things quite simple. just going to type it out here quick. Okay, so the vertical line test for a function. We know a graph represents a function when no 2 points on the graph lie on the same vertical line. Okay, so if 2 points lay on a horizontal line, it will work. So that is acceptable. If 2 points lay on the same vertical line, it is unacceptable and that will not be a function. If we're looking at our first graph here, we can see that no 2 points lay on the same vertical line. Therefore, this passes the vertical line test and it represents a function. In our second graph here, this one has an overlap of points that will fail the vertical line test at x equals 400 here, or mass equals 400. Therefore, this fails the vertical line test and is not a function. All right, in our next examples here, which of these graphs represents a function? Justify your answer. Again, we're just looking at our vertical line test. This function passes our vertical line test at every point. This relation, I should say, passes the vertical line test. Therefore, it is a function. This graph does not pass the vertical line test at a few different points. Again, it only has to fail at one. Therefore, it is not a function. So seeing data on a graph is really helpful to decide whether or not it's a function. I find it easiest to look at, but again, it's up to you how you'd like to represent it. Sometimes if I'm given ordered pairs or a table, I'll actually roughly graph it so I have an understanding of what that looks like. Determine the domain and range of the function, in each function. So we've looked at domain and range as discrete values. However, in this case, we have continuous data, so it may look just a little bit different. So we're looking at the domain, which is our x values here. This graph starts here, goes up and down, and this means that it's going to continue on in this direction for a long time, forever. Okay, what we know is that we don't draw arrows in math, but I'm doing that just to be helpful here. So we are constrained. It cannot go greater than x equals positive 5. However, it can go on forever in the negative direction. So what we're going to say for our domain is that x must be less than or equal to 5. If this point, like it is colored in, that means it can equal that value. If it is a open point, just a circle in this case, we would have said that x is simply less than 5. It cannot equal that value. Okay, our range. So in this case, if we're looking at the y-axis, that's where our range is. It can go on forever in the negative y value, again, because that is moving in forever in that direction. However, it cannot be greater than positive 2. So y must be less than or equal to 2. In our second graph here, we are constrained between 2 points. Okay, so our x values must be between negative 3 and positive 5. So I can say that x is greater than or equal to negative 3, and I can say that x is less than or equal to positive 5. I want to put these two together in a domain statement. So I'm going to put x in the middle, my larger number at the top, my smaller number below. I have x is less than or equal to 5 written in the exact same direction here, but now I have x and negative 3 written oppositely. So I need to flip this one. I'm going to write negative 3 is less than or equal to x, and that is the relation I'm going to put in there, or the inequality, sorry. For our range, we are stuck between positive 3 and positive 7. So I'm going to have to write another less than or equal to statement here. So 7 is the highest and could go, positive 3 is the lowest. So if I'm not going to write these out, I'm simply going to look at this side of my inequality first. So y has to be less than or equal to 7. All right. it can be equal to 3. And what I do is I just copy the direction that the inequality points here. All right. They always have to point in the same direction. So if I've already made this one, I can copy the direction over here. That's just a little trick. Again, if you need to write these out, I highly recommend it to put it together into a statement. We cannot include 2 of these. If it has to be between 2 values, you must write it in one inequality. All right, this graph shows the approximate height of the tide, h, meters, as a function of time, t, at Port Clements, Haida on June 17th, 2019. Identify the dependent and independent variable. So the dependent variable is the height of the tide because it depends on the independent variable of time. So time, nothing influences time, so it is independent. So independent was time, which was measured in hours. And the dependent variable was the height of the tide, which was h in meters. Why are the points on the graph connected? Well, if I look at the data plotted on the x-axis, time can be a decimal value. There are, we know that there are pieces of time between 9 and 10, 10 and 11, 11 and 12, 12 and 1. All right. So time is continuous as a data set. The height of the tide is also continuous. It creeps up slowly. It doesn't just go from 8 meters to 1.2 meters instantaneously with no in between, if you will. So because the height of the tide is not discrete and time is not discrete, they are both continuous sets of data. So time and height of tide are both continuous data sets. So it is a continuous graph and we can connect the points. Determine the domain and range of the graph. So again, domain is our x values. It looks to be here that we are constrained between 0900 and this is 13, 14, 15, 1600 hours. Okay, so x in between. It can be less than or equal to 1600 hours, and therefore it can be greater than or equal to 9 hours. So again, I've just looked at my right side of the inequality and used that and copied the sign here. For our range is our y values. So it looks like we can go to about halfway here and about halfway here. So each one increment looks to represent 0.2. So if I go up by half, I'm going up by 0.1. So 0.1 greater than 0.8 here. My low value is 0.9 meters. And my high value, this is 0.2, therefore this is 0.4. Halfway is 1.5. So y is in between those, and they can be less than or equal to. All right, here's a graph of the function g of x equals 4x minus 3. Determine the range value when the domain value is 3. So we're just reading the graph here. When our domain value, meaning our x value, is 3. So at x equals 3, we're going to look up at our graph, and we cross at x equals 3 at this point here. So we're going to read back to our y-axis. That looks about halfway between these. Each increment on our graph looks to represent 2. Therefore, if we are halfway up, that is up by 1. So I would say the range value equals 9 here. Okay, we can also calculate this if you wanted to, because we were given the actual function itself. So I'm just going to write this up here, y equals 9. We read that from the graph. We can actually input that into our function here. So g of 3 is equal to 4 times 3 minus 3. 4 times 3 is 12. Take away 3, which is 9. The exact same value we got. Determine the domain value when the range value is negative 7. So range value is y. So when y equals negative 7, I can read that from my graph here. That would be approximately here. So moving across my graph, and then read where that lies on our x-axis. That seems to be x equals negative 1, read from my graph. If I wanted to solve for that, when y equals negative 7, that means g of x equals negative 7. So y equals negative 7, therefore g of x equals negative 7, and we're going to solve backwards for x. So negative 7 is equal to 4x minus 3. To get x by itself, I'm going to do BEDMAS backwards. So I'm going to take care of the addition and subtraction statement. I'm going to add 3 to both sides. I'm going to get that negative 4 is equal to 4x. To get x by itself, I'm just going to write it up here again. I need to divide by 4. 4 divided by 4 is positive 1. Negative 4 divided by positive 4 is negative 1. So x equals negative 1. So we can do that by reading the graph, so interpolating from our graph, or if we have an actual function equation, we can solve for it. So how do you decide whether to connect the points you plot on a graph? We need to decide whether the data is continuous or discrete. So if it is discrete, it means they're instantaneous points and there's no in between. There's no decimal values between, and they're not connected. If a data set is continuous, meaning it can have any value of points, it's not restricted to the whole numbers or what's represented as the points on the graph, we can connect them because they are continuous. What can you tell about the domain and range of a function from its graph? We can tell the maximum and minimum points, all right? And how can you identify whether a graph represents a function? We're going to use the vertical line test here.